In this video, we're going to review and amplify some of the ideas we've covered in the last few videos, looking specifically at KDs and at saturating binding curves. And the reason I wanted to do that is because this is one of those basic skills in biochemistry that's going to be used over and over and over. So it's worth some time up front to really make sure that it's solid in our minds as we go forward. So let's get into this. I can do that. There we go. Biology is a big fan of non-covalent interactions. All kinds of transient interactions form between molecules that are important for governing cellular behavior. And if we're going to understand that, we really need to have a good handle on things like equilibrium constants and saturating binding curves. So the way I'm going to structure this video is we are going to do a quick review of things we talked about in the last video, thinking about dissociation constants and binding curves using the estrogen receptor once again, so it's in familiar ground. It'll be just a quick pass through things we've already covered. And then we're going to transition and use these ideas to think about something we haven't looked at before, which are GLP-1 drugs and their binding to the GLP-1 receptor. So let's get into it. Okay, so very, very quick reminder, the steroid hormones, steroid receptors recognize steroid hormones and activate transcriptional programs in response. So here the estrogen receptor binds to estradiol, translates to the nucleus where then it upregulates the transcription of various genes. Part of this process we're thinking about right here is that binding between estradiol, the steroid, and the estrogen receptor. And in the last video, we asked this question: how do we measure the strength of the non-covalent interaction between the estrogen receptor and estradiol? And we also asked the question, what concentration of estradiol do I need to see in effect? And it turns out that these are related to each other, that both of these are quantified, measured, and otherwise can be answered using this idea of a KD, a dissociation constant. And this is intimately related to this idea of fractional saturation. This measures what fraction of the receptor molecules have estradiol bound. This value ranges from 0, apparently pen's only half writing, 0, where there's no bound receptors at all the way up to 1, where all of the receptors are bound with estradiol. If we look at a curve that shows what's the concentration of X, what's the concentration of estradiol in this case, versus, on the X-axis, and then theta, fractional saturation on the Y-axis, we get a curve that looks like this. It starts low, comes up, and saturates. So this is the first of our kind of review points. What I'd like you to think about is, what does this tell us about the system? Why does this curve not just keep going up forever? So if you want to think about it, you can pause, unpause. So the reason it stops going up forever is because something has run out. Anytime you see a curve in a biochemical context where it starts and then levels out, that's saying something somewhere has run out. In this case, what's run out is the receptor, right? We just don't have any more receptors to bind to estradiol. All of the receptors are now bound with the estradiol, the steroid. So where, you can't make the curve go any higher. Okay, cool. The KD is the concentration in X that gives the half saturation. And we can describe it using this simple relationship that the fractional saturation, the theta, equals the concentration of our X, in this case estradiol, over KD plus the estradiol concentration. And so here's another point to pause. How would you graphically estimate KD from this curve? So why don't you pause and try to do that? Unpause. So the way you go about this is you draw a line that's, hits the y-axis at 0.5. Then you drop that line down to the x-axis and say, where did I hit? It's a little difficult on this curve to be very precise because, there's not a lot of lines, but this turns out to be 0.1 nanomolar. At 0.1 nanomolar, we are at the half saturation point. So that is our KD. Okay, cool. If you look at the reference values for an adult human female, the reference values for blood estradiol concentrations range from here to here, these black arrows. So why does it make sense? A good review here. Why does it make sense for the physiological concentration range of the molecule that binds to bracket the KD? So why is that? Pause, think about that. Unpause. Why does it make sense? It makes sense so cells can respond, right? this allows the cell to go from, oh, I'm, at low estradiol concentrations, I'm not bound. At high concentrations of estradiol, I am bound. And this whole thing in the middle, now the cell is basically measuring the concentration of estradiol in the blood based on this curve here. If the estradiol concentration was, all really, really, really low, this receptor would never bind and it would never know estradiol was around. And if the estradiol concentration was really, really high, the cell couldn't tell that the concentration was changing because it would always be loaded. So you see this all the time where the concentration of the physiological molecule that binds to the protein is right around the KD, the dissociation constant. Okay. Now we're going to do a drawing exercise. So what I would like you to do is draw a curve for a molecule that binds to the estrogen receptor with a lower affinity, and then a matched curve for where the molecule binds with a higher affinity. So again, chance to pause and think about this and do it on a piece of paper. So pause. Assuming you did that, we paused and unpaused. So the lower affinity, what that means, it's going to take a higher amount of a molecule to bind to make it bind. So it's going to go this direction. So it's going to have a shift to the right. The KD is going to be higher because it takes more of the molecule to bind for it to bound, or more of the molecule around to see binding. So this is the lower affinity case. Higher KD. Wow, KD. And then on the other side, drawing a curve with a higher affinity, that's the one that's going to shift this way, right? It's going to take an even lower concentration of our molecule to activate. And so higher affinity, lower KD. And does feel maybe sort of backwards, but maybe just keep in mind, it's always going to be backwards. A lower KD is a higher affinity. A higher KD is lower affinity. Okay, we're almost done with the review, but one quick thing we're going to talk about is specificity. And this is actually a little bit new. I didn't actually mention this explicitly last time, but I talked about last time how estradiol, which binds and activates this receptor, has a much lower KD than testosterone, which has a much higher KD, lower affinity. And I made this graph here. And what I never actually said was how we describe the specificity quantitatively. And the typical way we do that is using something called the KD ratio, or just we'd often say the specificity or the preference. And so what we can do is do, say, KD for testosterone over the KD for estradiol. And if we do that, it's 10,000 over 0.1, which means there's a 100,000-fold, so we normally say it, 100,000-fold preference for estradiol over testosterone, right? So it prefers estradiol 100,000-fold to testosterone. Now, for those of you that are sharp-eyed or are watching everything back to back to back, you might have noticed that our KD for testosterone changed. In the last video, I said it was 100,000 nanomolar. I got a little excited typing zeros. It's actually only 10,000 nanomolar. So sorry about that. So the KD for estradiol is 0.1 nanomolar. The KD for testosterone is 10,000 nanomolar. The ratio of those two gives you 100,000. So there's a 100,000-fold preference for testosterone, for estradiol over testosterone. Last new bit here on this, and then we're going to go into GLP-1s. Just this is mostly a note. I'm going to make myself disappear. That's the wrong button. There, I disappeared. This is something that you'll come across in literature and various places on the internet, and so it's worth mentioning that the data on the left are the same as the data on the right. And so often when somebody's describing binding data, instead of using a linear scale on this axis, they use a log scale. So this is a log base 10 scale. And the thing that's really convenient about a log base 10 scale is you can see a much wider range of binding, right, of concentration. So this is 10 to the minus 14th molar up to 10 to the minus 2 molar. So we're covering 12 orders of magnitude of concentration. Here on this side, we're not even showing 1 order of magnitude. That's why we see, oh, this nice binding for estradiol. We see nothing for testosterone. And so if we look at this graph on the left, we can actually do the same sort of operation we did before to measure KD, but now we're doing it on a log scale. So I can still go to the 0.5% line, and then say, well, where does it cross? Oh, look, it crosses at 10 to the minus 10th molar, which is 0.1 nanomolar. Nanomoles are 10 to the minus 9th molars. So that is saying the KD is 10 to the minus 9th molar. And then we can look at the testosterone and say, oh, its KD is 10 to the minus 5th molar, which it turns out is 10,000 nanomolar. Right? So you see data like this, you're like, well, what in the world? The curve looks totally different. That's just because people have taken a log, and that log lets you see more data on one curve. And the nice thing here is, right, we can see the difference in the KDs for estradiol and testosterone. Instead of just estradiol binds, testosterone doesn't over this concentration range, we can say, no, the difference in their KDs is in fact this 100,000-fold difference. Okay, so there we go. Okay, I'm back. Cool. So that was our KD binding and review. Now let's turn to something new, and we're going to apply things we learned from the last video about KD, and actually the video from before that looking at binding specificity and interactions. On sort of a molecular scale. So, and what we're going to be talking about is GLP-1 drug binding. So we're going to talk much more later about sort of blood sugar regulation in our bodies. But for the moment, all we need to know is that our bodies maintain blood glucose in a fairly narrow range. And this is robust to all kinds of things. So if you don't eat for a long time, your blood glucose is stable. If you eat, your blood glucose spikes and then immediately comes back down. So it's a really finely tuned system. And it's really important that it's maintained because if you, say, have elevated blood glucose for extended periods of time, all kinds of negative outcomes can happen: stroke, cardiovascular disease, cataract, periodontal disease, nerve damage. And this is one of the reasons that diabetes, which is a dysregulation of this process, is so bad, is because it leads to all of these downstream consequences. Sort of functionally, the way that this works is the pancreas, the blood sugar regulation works, is the pancreas and the liver collaborate. And so we can think about the pancreas as a sensor. It's sitting there measuring the concentration of blood glucose. And if blood glucose starts to go up, the pancreas secretes the hormone insulin. And if blood glucose decreases, it secretes the hormone glucagon. Now, at this moment, particularly if you're, say, taking a class of mine, don't worry about memorizing any details here. We're going to talk about these systems in detail later. For the moment, just we just have to talk about the biology to understand the sort of binding parts. But okay, so blood glucose increase, pancreas secretes insulin. Blood glucose decrease, secretes glucagon. The liver, by contrast, responds to these signals. And so we can think about it as a reservoir or a water tank. So if the insulin increases, that says blood sugar is high, which causes the liver to take glucose in. So it says there's enough glucose around, there's too much glucose, let's start storing it for later. And if glucagon goes up, that says the person is hungry, their blood sugar is low, and so then the liver starts to dump out glucose, sort of lower the reservoir to keep the blood sugar at a fixed level. Okay, things like diabetes and metabolic syndrome disrupt this collaboration, and there are a variety of different ways this might happen. The most common way, if we're talking about sort of things induced by diet and sort of not genetically encoded autoimmune things, is actually that the liver becomes less sensitive to insulin. So it takes more insulin bang to get the liver to do the blood glucose uptake thing. And so that's why insulin injections might help, is because it's helping the liver take up its blood sugar more effectively. But overall, this is one of the primary pain points that happens in diabetes and metabolic syndrome. Cool. Well, not cool, actually terrible, but it's a cool metabolic system to think about. Okay, so GLP-1 is a secondary signal. Actually, it's a biological signal that also sort of adds fine-tuned regulation on top of this. And so if GLP-1 is this is a hormone that's produced by us, if GLP-1 is high, it actually produces, or it causes the production of more insulin. And this is a complicated network, which you will become intimately familiar with if you keep watching my videos. But GLP-1 activates this molecule called pKa, and then pKa goes on through a complicated series of events and then triggers the release of insulin. So independent of all the other parts of things happening in this network, GLP-1 activation here, insulin release here. And so we can think about it as a GLP-1 activator is supercharging insulin secretion. It's making the the pancreas secrete more insulin than it would otherwise, which is great because that's a harder, it's a stronger signal to the liver saying, no, you really should be taking up glucose. So turns out GLP-1 activators are a super amazing and helpful therapeutic. So first developed for diabetes, recently realized that it could be used to treat metabolic syndrome, even just for weight loss for treating obesity. And so this is a huge market. And I'm assuming that you've all at least heard now of Ozempic and Wegovy. If you watch any television or content online, one of these ads is going to pop up. And this is a $22 billion, or was in 2022, it was a $22 billion market. And the market whispering tea leaf readers at where was this? At JP Morgan are predicting it will be a $100 billion market by 2030. So huge market. There's a whole bunch of applications for this. These are really a cool drug is helping a lot of people. So what are we going to do? We're going to use this to think about binding and why it's important and the sorts of things that actually the people who built these drugs were worrying about as they built the drugs. And so this is a structure of the GLP-1 receptor, actually bound to an early version or a sort of midway along the developmental pathway version of the drug, this green drug. If you've heard of them before, this receptor is a GPCR, so it's a G protein coupled receptor. That's how its mechanism of action works. When GLP-1 drugs bind here, they bind in this deep pocket, and then that triggers downstream stuff. Now note, I'm drawing this in the typical biochemistry convention way of a dissociation reaction. So I'm showing it on the left associated, on the right I'm showing it dissociated, so it falls out. What we're going to think about now is let's analyze the binding, right? And so we're going to look at this from a variety of different angles. The first is this is actually data that I took out of this paper here looking at this drug. So what's the KD? And what dose would be required to get the GLP-1 receptor to 90% saturation? So this is one of those things where it's good, pause and think about it for a second. So pause, what's the KD and what's the dose? Pause. Unpause. So what's the KD? Well, what do? We go to the 0.5 line, right? And then we drop down to the x-axis and say, what is that KD going to be? And it turns out it's going to be 8 nanomolar. So the KD for this drug is 8 nanomolar. The dose required to get 90% saturation. So for that, you go up here and you say, well, there's 90%. There's a 90% line. And if I follow this line down, see if I can actually draw in a coherent fashion, it's going to be about 25 nanomolar. Right? So if we can get the drug in somebody's blood up to 25 25% nanomolar, we'll be at 90% saturation of the receptor. All right, cool. Can we relate this to the structure in some way? So here we've got that structure. That was the paper actually that this came from. They were solving the structure of GLP-1 bound to this receptor. So let's make some predictions. All right, so I'm showing the molecule here. This is the drug from both the front side and the back side. Yeah, I'm not in the way. Carbon atoms are green in this structure. White is protons, red is oxygens, blue is nitrogens. So what sorts of interactions might this form, and which regions can form those interactions? So again, here's a moment to pause, think about it, start work on your structural reasoning. So pause. Unpause. Okay, cool. So what I observe here is look at that. That is all hydrophobic, right? It's just a bunch of carbons. There's not a lot of things like oxygens around. There's no electronegative atoms that would be polarizing bonds to make hydrogen bonds. Same sort of thing here, right? There's a big chunk hanging off that's just hydrophobic. But then on the other side, the back side, we see this giant array of hydrogen bond donors and acceptors. So everything, this right here is a hydrogen bond. That did not come through the circling very well. Sorry, this one right here is a hydrogen bond acceptor, right? There's no oxygen on it. Let's see, this one here, this is a hydrogen bond donor. And we see this region here. In fact, those are kind of one contiguous region in the molecule of hydrogen bond donors and acceptors. So what we would predict is if you put this into the pocket and it's binding well, it's going to be able to find both kinds of interaction. So indeed, we see that. So what I've done here is I'm showing all of the hydrogen bonds that are formed between the drug in green and the receptor in blue, or purple, slate, whatever color this is. And hopefully, you're like, look, there's lots of hydrogen bonds that are being formed. There's actually some over here. So the receptor is in fact binding with forming lots of hydrogen bonds with the receptor or with the drug. We can also see hydrophobic molecules. So this is a different view of the drug, just from a different angle in the pocket. But hopefully what you appreciate there is we've got this big hydrophobic brick here, and the receptor has a bunch of carbon atoms itself that are all sitting down binding to that brick-like region. So there's lots of hydrophobic interactions. Incidentally, this is a good point to put out. You're like, well, yeah, what's happening to that oxygen there? Remember, we talked about how it's really bad to lose hydrogen bonds. Turns out this is actually facing right out into water. So water molecules can all come in here and interact favorably with that oxygen. Okay, so here's another point. We did some structural reasoning looking at the structure. Now let's just think about it. Which interactions are going to be important for making the drug stick in the pocket, and which interactions are important for specificity? And maybe implicit in that is a question of why. So this is a good point. Think about that for a moment. Pause. I'm going to unpause. And what we're going to see, or what I would argue, is these are important for sticking. This is the hydrophobic effect, right? And the reason the hydrophobic effect is important for sticking is because those interactions are unfavorable. The exposure of those surfaces is unfavorable in water. If you can stick together the two molecules, you can you can release the water molecules, making a new favorable interaction. That's a very favorable sort of thing to do. And so generally, anytime you've got hydrophobic stuff in solution, it's going to clump together just naturally. But then these over here are important for specificity. And these are the H bonds. And the reason they're important for specificity, right, is if the hydrophobic effect is causing things to collapse together and you don't fulfill your hydrogen bonds, that means you're losing hydrogen bonds you made with water. That's unfavorable. So making complementary hydrogen bonds is really important for building a specific interaction. And remember, we saw that for the estradiol and the testosterone. Estradiol and testosterone just differ in a little bit of hydrogen bonding capability, and yet testosterone binds 100,000 times worse than estradiol just because it can't fulfill those hydrogen bonds well. Okay, so we can summarize that idea just to make sure it's all in our brains, that nonpolar and polar interactions play different biological roles. Hydrophobic things, nonpolar interactions tend to make molecules stick together, whereas polar contacts tend to make only specific molecules stick together. All right, so now let's go think about the drug design process. So this GLP-1 drugs are actually derivatives of naturally occurring molecules. And so they started with a natural one and they started modifying it over time. So here's drug number 2. This is actually predates drug number 1. So this is an earlier version of the drug. It's missing this big hydrophobic chunk here. So what do we think? What's going to be the loss of that hydrophobic chunk going to mean for affinity, for KD, and Y? So what does removal of that chunk mean for affinity, KD, and Y? So here's a moment. You can pause and think about it. Okay, unpause. It's going to lower the affinity. We'll talk about Y in a second. It's going to raise the KD, right? The KD is going to be higher. It's going to take more of the drug to bind the knot. And the reason why is you lost favorable hydrophobic, right? You lost stuff that's going to naturally make the protein and the drug stick together. So it's just not going to have as high of an affinity. All right. So we actually can see that. Here is a graph of drug 1 and drug 2 with their binding constants measured. So what's the KD value for drug number 2 and what's their specificity? So this is another moment. You can pause and think about it. Okay, we unpaused. So recall the KD for this one was 8 nanomolar. If we drop down. For this one, it is... That was a terrible drawing, but it's about 50 nanomolar. And remember, the specificity is just going to be the ratio. So it's going to be 50 over 8, which is 6.3x. So there's a 6.3-fold preference for drug 1 over drug 2. So it's not nearly as crazy as, say, the estradiol versus testosterone, but there is a higher preference for drug 1 versus drug 2. Finally, these are, like I said, were developmental drugs. So this is, from I guess 2017 was when they were working on drug number 1. The GLP activators that are now on the market have even higher affinity. Why is higher affinity generally better in drug design? So this is something drug designers work really hard on, increasing binding affinity. So why? What's the reason for that? So again, here's a moment to pause and think about it. Unpause. So why is it higher? Why is it better? It says lower dose, same effect. Right? If your KD is higher, or sorry, your KD is lower, you need less of the drug to get the same activity. These drugs are both, that's both good for the patient, right? You want to give the patient as low of a dose as possible. It's also good for the companies. These are what are known as biologic drugs. So they're extraordinarily expensive to make. So the less you can put into your treatment or your injection, the more money that you can make. And it turns out capitalists like making money. So they like increasing the affinity or lowering the KD of the drugs. Okay, so that's all I got on this. Hopefully that was a helpful review of binding constants and some, using them in situ. As we go forward into different content, we're going to run into all kinds of different places where suddenly, oh, look, KD appeared. Oh, look, a saturating curve occurred. It's something definitely worth your time to invest in and think about and work on. With that, I will talk to you later.